do here is I like to start out and just say, hey, we're going to go into sequences in series today. This is chapter 11 in your book. The way that the new standards and stuff that are aligned, it's the first unit that we're supposed to go into. So we'll just start with that. I don't know. There will be parts in here that in this chapter that there will be some equation stuff that you're going to have to solve. You're going to have to solve some stuff that you have not done before. And when that comes up, I will walk you through it and introduce you guys to maybe a little bit of what's called a logarithm. It's basically for some of these things, we're not going to do the full onset of logarithm. What we're going to do is we'll do the problem where you have 5 to the x equals some number. And we're going to solve for this. How do you solve for the exponent? That's what we're going to work at. We're not going to use the actual logarithm itself yet as far as graphing and doing all that stuff, but we'll get to that point. So today what we're going to do is we're talking about what are sequences in series. You guys have worked with this before, okay? Believe it or not. What comes next? 2, 4, 6, 8. It's that easy. 3, 6, 9. Yes. I think it's 1. I don't know. There's one called the Fibonacci. I don't even remember it. Anyway, the Fibonacci sequence things. So here's what we have. You have I have 2 sequences up there. What is the difference?
One's continued.
One is what?
Continues.
One continues. So one continues on and on and on. The other one stops, correct? Everybody agree on that?
Yeah.
This would be, when something continues on and on and on and on in math, what do we call that? Infinite. It's continuous. Yeah, it's infinite. Line. Yes, it is a line. Yeah. So these guys in here, these parts, are called terms. So this is term 1, term 2, term 3, 4, 5, whatever. That's the number in the sequence. Think of it in terms of domain and range. You guys remember domains and range?
Yes.
What's domain and range?
I know the range.
What's the range?
It's the biggest number minus the smallest number. Isn't it?
No, you're thinking
What is it?
you're thinking distance. You're thinking in absolute value stuff.
I don't know.
You just said it. What is it? You just said it, I think.
Me?
Yeah. No. What's your name? Haley?
Izzy. Well, I was
Daisy.
Izzy.
Izzy.
Daisy.
Correct. Domain and range are your x and your y values. Do you remember which one goes with which? No.
X is domain.
What comes first in the alphabet, x or y? What comes first in the alphabet, domain or range? Therefore, x goes with and y goes with. It's the easiest way to remember that. You may not remember anything else about domain and range except that if you know which one comes first in the alphabet. I hope you guys all know the alphabet. Do we? Should we sing it? You can. Would you like to? All right, there we go. A, B, C, D, E, F, G, H, I, J, K, L, M, N, Q, R, S, T, U, V, W, X, Y, and Z. Now I know my ABC. Next time I'll sing with me. Yay! All right. Now, this is where I want you guys. Yeah. Every once in a while we turn out to be a bunch of idiots, but that's okay. This is where I want to introduce you guys to how to use this calculator. A lot of times when we're talking about terms of sequence, we use what are called, you guys ever see this?
Yeah.
What's that called? Subscript, very good. It's subscript, okay? That subscript is, when you say is A sub n, excuse me. That n value is in relation to the number, the number in the sequence. Which term is it? Is it the first term, second term, third term, and so on. It's the x value to generate the y value. Does that make sense? So when you say this is a sub n, and I want to start out with the first 6 terms of the sequence, well, when I start with the sequence, the first term would be term number 1, term number 2, and so on and so forth. So what I'm doing here is I'm going to let n equal 1, 2, 3, 4, 5, and 6. Which means I have to substitute in 1, 2, 3, 4, 5, and 6 for n within that equation. Well, that's not going to be so bad with this first one. 2 times 1 plus 3, 2 times 2 plus 3, and so on. You could probably do all of that in your head. So what's that? 2, so you get 5, 7, 9, 11, 13, and 12, 15. Everybody okay with that?
Yeah.
Or is that too much work to handle on a Tuesday?
Wait, today's too sweet.
There you go. Take out your calculators real quick. I want to show you guys how you can do these things in your calculator to make your life easier. Lake Superior. Thinking. Eventually it'll load. There's this crazy button on your calculator called y equals. Seriously? Now, if it says y equals, isn't that looking for your range?
Yes.
Oh, there it is. Okay. So when I'm looking at this and it says y equals, here's what I'm going to do. When I hit the y equals button, it opens up a place for you to put something. I'm not going to worry about that function. What I'm going to do, I'm just going to substitute in 2x plus 3. That x value, the variable, is right next to the alpha key. The alpha is the green one.
It's the one right in.
It's the second one over. All right? Everybody see that? That's your unknown. That's your variable. The calculator uses x. All right? So now just go to table. How you do that is you hit second graph. Now, with your guys' calculator, depending upon what the settings are, your table might start somewhere else besides 1. Does anybody have a table that's not starting at 1? What's your table setting at? Starting at 1329. Okay. Now, if your table is starting at something weird, let me backtrack here. When you guys first learned how to graph lines, did you guys always graph a couple negative values, 0, a couple positive values? So you had a good looking of what was going on about the y-axis? I don't remember what that was called. Do you vaguely remember that? Yeah? Okay. Here's what I want you to do. I'm going to show you guys how you can set your table to help you work through these things. On your calculator, if you hit second window, it allows you to set up your table. It should come up with table setup. Everybody see that? Yes, sir. Yours, I know, I'll get yours fixed up, don't worry, all right? So now, right there, mine's starting at 1. And I have it set for that because I'm working with sequences in series, just because I know that I'm not going to have a sequence starting at 0, it's going to start at the first term, and so on. So that's why I had it set at 1. Go ahead and change yours to 1, and you should be just fine. All I have to do is hit 1, hit enter, and then you can go right back to your table by hitting second graph. And it should look like that. Didn't work? Why not? Bless you. Oh, you got to put them on auto. You want your independent and dependent to be on auto and not spit it out. Okay? There's reasons why we changed that, because you can actually substitute in a specific value and spit it out for you. It'll generate, so if you wanted to substitute in 7,413, you can put that right. Your equation. Your equation's all weird. I don't know why. Yeah, it's just, I just cleared it out and it worked out just fine. Everybody okay with that?
Yes.
Okay. Now, here's what I want you to do. I want you to use your calculator and type that in. I want to see if you can type that in without too much of a hassle. Now, this is written as function notation. You guys have all seen that, right? F of n. So if you wanted to substitute in 1, you would say f of 1, f of 2, f of 3. That means wherever you're going to see the n, you would substitute in a 2, 3, and whatnot. So I want you to put that equation in, and let's see if you can figure out how to type that in correctly. Now, I haven't taught you how to use the superscripts, the exponent rules here or anything yet on those. Let's see if you can figure it out. This is not the longest section in the world to work with, but, oh, Mr. Fontana, could you get me out of test mode? Yeah.
I was going to come to who's the?
Yeah.
Borrow that real quick.
Do you need a calculator?
Actually, you know what? Let me go grab a cable. Here.
I got one.
The unit to unit, the small one.
Here's mine. You want a regular 84?
I need a regular Inspire. Nobody else has it. Does anybody else in here have Inspire?
Nobody else has that.
I'll be right back. Okay. All right.
Yes, sir.
My arrow keys don't seem to be functioning
Hey,
properly.
Why'd you drop your calculator?
I never dropped it.
I didn't never not.
I never did not want to hear, so that's a double negative.
Tell him to bring Gatorade, okay? What is he even bringing? I don't know, it's just liquid. Weird liquid in bottle. Sounds
And
appetizing.
with this kind of action, everything is negative 0.5.
Huh, yeah, yours not working. Your arrow keys don't work. Let's see if I can find a use a different face and see if that'll work. Did everybody get that to work okay?
No.
No, please no.
Yeah, I think so.
Yeah, it was just that faceplate. Faced it outwards. Works just fine. All right, so when you're typing this in, obviously you're going to type it in exactly the way you see it. When you hit that caret button, that jumps you up right away. Right above the division.
I didn't even see that.
Oops. Yes, sir.
Can I use that faceplate?
Oh, yeah, you probably want one of those, don't you?
Make sure he does this and yell at him if he doesn't. Boom. You don't want to see this, right? You want to see that? Right?
Exactly. Thank you. No. X minus 1 is the exponent. I know, I couldn't find the y. I know how you did. Evelyn, look at what you did.
All right.
It's off.
Everybody find that button then?
I'm sorry, my shoe came
Sorry.
off.
And then what was it? X minus 1, I believe? Yeah.
See, he did the X, Evelyn.
Now, what's nice is that you can type it exactly the way that it's written in the book or on an example. As long as you use those superscripts and stuff, the calculator allows you to do that. Last year, most of you guys probably used that multi-view calculator, the TI multi-view,
Yes.
where we just simplified the radicals. This is the same basic keystrokes. It had that.
Someone dropped it.
It has the same basic idea where you use the arrow keys to get you back and forth. Now, to go to your table, just hit the second table, and again, it just spits it right out for you. It'll give you your values.
I got that right.
What's the first term?
One.
Well, no, hold on. What's if you look at the original equation itself was -2 to some power. So what's -2 squared? +4. Negative 2 cubed would be negative 2 times negative 2 times negative 2, which gives you the negative 8. That's why it alternates itself back and forth. All right? You'll mess around with positives and negatives today when we start to determine if you can write your own sequences and stuff out. Okay? Does that make sense as far as how to use the calculator? All right. We'll come back to that in a second because there's other trick we're going to work on. I'm not going to mess around by putting more of these in here. But now what I want to do is I want to start to do what's called writing a rule for the nth term. Now, what you guys were doing was a minute ago, you were working with the nth term. You were working with the rule, the generic equation. A sub n was 2n plus 3. That was the rule. Your first term was 2 times 1 plus 3. It gave you 5. Now we're going to try to figure out how can we write these sequences out in terms of some generic equation, some default equation, if you will. This is where it takes time to recognize the pattern. Now, if you haven't worked with exponents in a while, or you don't remember exactly how things set up, it's okay. It's going to take a little bit of time. Now, what Hannah was asking a second ago about the whole, why were the signs changing? If you notice that first sequence, see how the signs are changing from negative to positive, negative to positive? Okay. What's happening there is in order to change from positives to negatives, you'd have to be multiplying by something by a negative each time. Or a lot of times if you follow the pattern here, 3, 9, 27, 81, what's happening?
Negative 3.
Well, let's just look at the terms, the values of 3, 9, 27, and 81.
Times 3.
Right. 3 times 3 times. So in other words, if I write that in terms of an exponent, that's 3, 3 squared, 3 cubed, 3 to the 4th, and so on. You okay with that?
Mm-hmm.
All right. Now, does that change if you put this here?
No.
Correct. It's just writing it out differently. It's just writing it in terms of a fraction then. Now, what's happening here is since your signs are changing, your first term was what? Yeah, your first term was negative 1/3. So that means my rule, my basic rule, my a sub n, was my first term raised to the n value. Does that make sense? The first term was negative 1/3 raised to the first power. The second term, negative 1/3 squared, which is 1/9. Third term is negative 127. It's negative 1/3 cubed, and so on. It'll take a little bit of time to recognize some of the exponent problem ones where you're working with fractions, because you just haven't worked with them in a long time. What's going on in the next one? What's a little trickier? Yeah, but could you figure out what the pattern is, though? What is the mathematical pattern? And this is where things get weird. You guys remember geometric and arithmetic sequences? You ever heard of that?
Yes.
What was it? Do you remember the difference? An arithmetic sequence is where you're adding the same value each time. Geometric is where you're multiplying the same time. This happens to be neither. There's some weird pattern going on here. And it's okay if you don't pick up on it right away. They're not the most obvious sometimes. They don't wind up being as clean as it would be like them to be. Now, 2 is the first term, right? 6 is the second term. 12 is the third term. What is it?
I can't, was like you square it and then you minus like this, like, so like 2 squared is 4 minus 2, 2, and 3 squared is 9 minus 3 is 7. 4 squared is 16 minus 4. That's how I got it.
Oh yeah, that works. All right, that's good, that's good. What do you got?
You got 2 more, like,
You're adding,
the first one's plus 4, and that's plus 6, and that's plus 8.
okay. And then the next one would be
Plus 10.
plus 10. So would that work out for the next term? So you were saying, so it'd be, so I want to write out your squared one. What was that again? I forgot how you said it. So it's a sub n. So you're starting out, your first term was
Minus n squared minus
n squared minus n. Okay. So that 1 squared minus 1 gives me 0. That's not my first term though, is it?
N plus 1.
Okay. But I see where you're going with that though.
Works for
When n starts at 2.
me. I'm sorry too.
Now, there's a cheater way around that, and that's called, we'll talk about, that's when we use summation. We could go your route that way. But you see what I'm saying?
Yeah.
You're developing it out that way. Now, think of it in another way. Think of it as your first term, your x value, and your y value. Your x value is the first term is 1, your second term, third term, fourth term. It generates, I almost got it. It generates 2, 6, 12, and 20. See if you can build with that. Where you at? Is it n squared plus n? So if it's n squared plus n, gives me 2. And so on. Yes, ma'am. Glad I could help. See how close you were? And that's the whole idea. Sometimes just by rewriting it out like this, you can start to mess around with it a little bit to see how it goes. And what's great is that you have a calculator, right? That has a y equals button. Could you test your hypothesis as to what you're thinking the pattern is going to be in terms of n? Just by going right to the calculator at the table again. If you type that in, it'll spit out. If you type in your equation, check and see if you're right. It's just a matter of can you develop with the patterns. Okay? And you're right by saying that you just had to ask what's the next term in the sequence. You're fine. You knew you picked it out. Plus 4, plus 6, plus 8, to be plus 10, plus 12, and so on. And that would be fine. Because a lot of times, like on the ACT tests, they're going to ask you what's the next number in the sequence. They're not going to ask you to develop all this. They're going to know that. And you pick up on it? Perfect. All right? Not bad? All right. Good. Breaking your brains back into math, right? Yes, ma'am.
How do you do a fraction
Alpha y equals. If you hit alpha is the green button, y equals, then it comes up with that table, if you will, and it gets you the fraction bar. It'll look identical to the multi-view then. Okay? It's just going to take a little bit of time to get used to it. All right, let's look at this side. The difference between the sequence and the series is very, very obvious.
Those dots.
Nope.
Look, the plus sign.
The plus sign. The difference between a sequence and a series is that in a series you're adding up all the numbers within the sequence, whereas the sequence you're just listing them all out. Okay. This is where that summation notation comes in. So the difference between them is basically just these addition symbols. Okay. You guys talked about this earlier, the infinite sequence, when you have that continuation, the dot, 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 that's the infinite sequence, or you can have an infinite series as well. We used to, I don't think we're gonna do that this year, but we used to be able to figure out what would all the numbers add up to equal within an infinite series. There's a formula to figure that out. Which is weird when you start to think about it because it's infinite. How do you know how much they're all going to add up to equal? It's magical. It's not infinity. There's a formula to set this up. So when we're talking about writing things in terms of series, we introduce you guys into what's called sigma notation. The silly Greeks. What's that? Yep. That letter, it's the Greek letter sigma. In math, it means sum. The sum of a series. It means, in math, we use that as for sum. So in this example here, if I want to look at this finite series, I'm just going to look at this one, this example. How many terms are in that series? 5. There's 5 of them. So the number of terms in this series is 5, so that number goes here. It starts with the first term. So I'll say n equals 1. So I'm starting at the first term in the series, going through 5 of them. And what's the pattern for that series? What's the rule for the nth term here? Yeah, 3n, 3 times n. 3 times 1, 3 times 2, 3 times 3, 3 times 4, and so on. It would be this. That's how I would write out this series in sigma notation. I'm starting with my first term. There are 5 terms in that series. What's the explicit rule? What's the rule for the n terms of n? It's 3 times 1, 3 times 2, 3 times 3. Now again, we could just find out what that equals by adding 3 plus 6 plus 9 plus 12 plus 15. That's not that difficult to do because there's only 5 terms. Well, what happens if there's 25 terms? 35 terms? You would cry, wouldn't you?
Probably.
What if I told you there's a button for this?
I would.
Button? Yeah, there is. So let me show you how you use sigma notation. Okay? Alpha window. And I believe it's number 2. Look at that. Okay? So it will do summation notation for you in the calculator. So it'll type in, here's where we're going to put your variable. X equals 1. You're starting at the first term. Hit the arrow button to go to 5. And then inside the parentheses, you type in your rule. Everybody got that?
45. Yes.
And you hit enter.
Why do I keep Is there
There is not an infinity button. There is a specific formula to solve the infinite series, but we're not doing that, so you don't have to worry about it. So anytime you have one of these types of problems, you're trying to find the sum of a series, you should never, ever, ever get that wrong. Ever, ever, never. Okay? Because there's a button for that. Okay? It makes life easier. Okay? What's going to be difficult for you guys is to come up with the actual rule for some of these. Now we just did this. So see if you can figure this one out. What I want you to do is write each series out into summation notation with sit notation. Try to write it out. Now, you'll notice that there's a starting point and an ending point for this one. That means there's a specific number of terms within that series. The number of terms in the second series is infinite. So what's going to go on top of the E?
20.
The infinity sum.
Oh, what?
Exactly. Since this is, we don't know how many terms are in this because it's continuous, I know that it's going to start at the first term and it's going to go through infinity. I know that's what that will look like. Here I know it's going to start with the first term and it's going to go through so many of those. You have to figure out how many it's going to get there by figuring out the rule in terms of n. You'll find out it's really not that complicated. What's that?
I keep writing regular M's.
It takes a while to.
I think it's right.
Do what?
I'm pretty sure it's right.
Was it? Yeah, you just fine. Don't forget the other one. I got you halfway through the other one. Did everybody agree? Does everybody agree on this first one? It's 5n, 5 times n. So I know it's going to go through here. How many terms are going to be in that sequence? How did you figure that out?
5 times 20 is 100.
Yep. 5 times 20 is 100. Everybody okay with that?
Yes.
I know some of you guys substitute that already in the calculator. What did you get for your answer?
1050.
1050? Everybody okay with that? Now, what's your rule for the one with the fraction?
Oh, yeah.
Excellent. You guys see n over n plus 1. You're starting with the first term, so your first term would be n. N is 1. So if it's 1 over 2, it's n over n plus 1. The second term, it's 2 over 2 plus 1. 3 over 3 plus 1. So you get the pattern of n over n plus 1. Does that make sense?
Yes.
What do you mean no? The weird, like I said, the weird ones are going to be when they start to involve some of the exponent rules. You have to see if you remember any of that. There is no infinity button on your calculator. You can't figure this out. Why? No, there is an answer.
But depending on.
It depends upon a couple of factors, and we're not really involved in this. We're just going to write it out. And we did this, blah, blah, blah.
What?
What? We already did it.
No.
What?
I was thinking something different. Go on, it's okay, I'm not doing it anymore.
All right. Do we need to spend time in letting you press buttons on your calculator to figure out the sum of that series?
What series?
This series.
That series?
The fact that they use an I, are you okay with it meaning the same thing as X?
Yeah.
No, it's not.
It's not the imaginary number yet. We'll get to that. You know there are imaginary numbers, right?
Yes.
Yeah.
Okay.
No.
Like 11 billion?
No.
Okay. Do you think you could type that into your calculator without too much of a hassle? Okay. Mr. Freeman. A little bit later. 1040. Now, in this case, they're starting with the first term at what? 3. That's all. Instead of being at the first term, they're looking at the first term being 3. So instead of going x equals 1, you do x equals 3. Just read the problems carefully if you have to figure out some of these problems. Some of these, it's really, really straightforward. Oh, I've all screwed it all up. I know.
Yeah. Yeah.
Don't always trust me, because I'm usually not that good at this.
Oh, I see.
Did I ever do this? Make it bounce.
Whoa.
Oh, yeah. You didn't know that? It's math magical. Last year.
Since you're a mathematician.
And then I can zoom in on that. Check it out.
What is that supposed to be? Highway.
Focusing.
Oh.
What if I want to focus on
Then you want to zoom it in a little bit more, make it more important. And then we'll look at it over here. Is there any reason for me to teach you these special patterns that you have to memorize?
Maybe?
No. You know why? This book was written before you guys had fancy calculators. There is absolutely no reason to memorize these style patterns. None.
So we don't ever have to do that?
No.
Okay. Right answer.
Because you would just put this in your calculator. Because when I ask you to write this out in long form,
Would you?
no,
Wait.
that's stupid.
So will we have to show our work?
No, there's a button.
So we don't
Get
have to show
over it.
any work.
You just can't get it wrong.
Don't get it wrong.
You get it wrong.
Here's what I want you to do. And this is where there comes into play where about making sure you don't get it wrong. A lot of times I give you guys the odd problems because you're right. A lot of these things you are just pressing buttons to check and see if you got it right. Now, there are some of these that you're going to have to write out the rule. When you go to write out the rule, I wanted to give you the odds right up front so you can check it to see if you're getting it right. See how close you are so you can play it back and forth. Now, the way that this works is that homework is up here right now. I'll put it up on the board on the side here. You could probably already see it if you guys walked in today and look on the north wall here. I have it set up. We're doing 11-1, 2, and 3. Then we're skip to 11-5 on Friday. That's going to put us basically done with this chapter in like 5 days. This 11-5 takes a little bit more time than anything because it's writing rules of recursive. So we'll probably blend this into a little bit of Monday. Do a little bit of review on Monday. Get out of this chapter next Tuesday already. So a week from today, you'll have your first test. Yeah. Yes, ma'am. Some days.
Some days.
It's usually a crapshoot. I don't really tell you when I do, but more often than not, I do.
Do we have homework quizzes?
Oh, those are sometimes.
I hate those.
A lot of what happens with the